Okay, we'll get started here. Real quick on the test, I went over the solutions right after the test, and I realized back when I was grading it that on the first one I had forgot something on the integration by parts. So you let u be equal to arctangent 4x, and then their dv should have been the dx, which means v is x. And then here's the part that I had messed up. du was 1 over 1 plus the 4x squared, but then I did not put times the chain rule, the derivative of what's inside, which is 4. So there should have been a 4 here also, dx. So I'm not going to go back and change the video I made over that. Just be aware that there should have been a 4 in there. And then the rest of it was okay. Now today, let me see, day 6. Let me get us going here. I want to just talk briefly about the exam because we have a lot to do. What the heck was that? Whoa. I'm going off of memory here, and I think I graded these on Saturday, or I can't remember what day I graded them. I believe that the class average on the exam was somewhere around a 70%, somewhere in there. And the standard deviation for the population was 23, we can say, percent out of 100. So if you know anything a little bit about statistics, then that's a pretty large standard deviation. It means most people would lie within 1 or 2 standard deviations of 70. So the grades were spread out, in other words. I don't remember how many A's, how many B's, how many C's, how many D's, how many F's we had. But I do know that the highest was 114. It's almost everything except one. I think I took 1 point off that exam. So the highest grade possible was almost achieved. I don't remember what the lowest was. So remember that this test, I believe, is 20% of your grade. So you can figure out on your own, where you stand now. You can go look at your quiz average and figure out, where you stand there. And we're going to have more quizzes, and obviously there's still a lot of grade out there still for you to earn. So if you didn't do as well as you wanted to on this first exam, there's still a ways to go. So reminder, no class Thursday. What's that? The 2nd, because of the holiday. All right. Okay, so last time we finished up, let's see, we were doing these, what do we call these? Integrals where we had infinity now as our limits of integration, right? Talking about probability density functions and wanting to have an area underneath it equal to 1. Remember improper integrals, right? And there were 2 types of improper integrals. And the first one, the type 1, note 6.61, is called infinite intervals. That's what we started with last class. And I did give you one problem to look at yourself. Did you have an opportunity to do this? Where is it? I think it's the one before this. I didn't bring it up. Let me bring that problem up. Did anyone try it and have any issues? Anyone get it? No? Yes? Good thing I didn't give a quiz over that, I guess. It was this one right here. I'll start class with that just to get us kind of going again. All right, so the idea here is that because our limits of integration are infinite, we have to split this up into two separate integrals. The first integral will go from negative infinity to where? Anywhere I want, really, but 0 is the one that I picked. You could pick any real number between negative infinity and infinity, if that makes any sense. Then you add to that another integral now picking up at 0 and continuing on forever. And then each one of those become limits, right? You have to replace your infinities with t's and then let t go to something. But in either one of these, or in both of these integrals, I'm going to have to know what the antiderivative of x e to the x is. So I'm going to go do that on the side over here. Just going to look at an indefinite integral, antiderivative of x e to the x dx. I'm going to use integration by parts. U is x, du is dx, dv is e to the x dx, and v is e to the x. So choosing my u to be x because it gets better as I take the derivative, and then antiderivative e to the x is itself. So this integral becomes ultraviolet minus integral of v du, and the antiderivative of e to the x is itself. So we get x e to the x minus e to the x plus some constant, but we already know that we won't use that constant once we plug into the definite integral. You could also, if you want, factor out an e to the x. Most textbooks would do that. They would factor out an e to the x and just leave the coefficients in front in parentheses. Okay, so now let's go back over here, and I'm going to go ahead and rewrite this. This first integral is a limit. I'm going to let t go to negative infinity of the integral from t to 0, x e to the x dx. So that's just by the definition. If you're going to do an integral going from negative infinity to a number, then you replace the negative infinity with t. You let t go to negative infinity. Then I do the same thing on the other one, except this time I'm going to let t go to positive infinity, 0 to t, x e to the x dx. Any questions? What I'm doing here? All right, now we would go find the antiderivative of each of these, which we already did. So this becomes limit t goes to negative infinity of the antiderivative, which is e to the x minus times x minus 1, evaluated from where to where? I need 0 and t, right? The way you say this, I mean, you can say this different ways. I always like to say it, you know, e to the x times x minus 1 evaluated from t to 0, because, you know, on a number line you're moving from left to right. You could say evaluated at 0 minus being evaluated at t or something like that, but as long as we understand the upper limit goes on top, lower limit goes on the bottom. And then plus the other one. And what, 0 to t? Now let's just plug in 0, see what we get, plug in t, see what we get, subtract the 2, see what we get. And then at the end of that, we'll take a limit. So limit t approaches negative infinity. Here's my bracket. Then inside the bracket, I know I'm going to have two sets of parentheses. All right, and the first set of parentheses is what I get when I plug in 0. So what do we get here? E to the 0, 1. 0 minus 1, negative 1. So 1 times negative 1, that's just negative 1, right? So negative 1 goes here. Now you plug in t. When you plug in t, that just becomes a t, and that becomes a t. So you get e to the t times t minus 1. Do the same thing on the other one. Two sets of parentheses. This time, I'm plugging t in first. So when I plug in t, I just get e to the t times t minus 1. And then on the other one, when I plug in 0, we said we got what? Negative 1. All right. When you let t go to negative infinity, it has no effect on this, right? But it does have an effect on this. So I'm going to rewrite this. Negative 1 minus limit t goes to negative infinity, e to the t times t minus 1. So what I'm doing is I'm just passing the limit through the brackets. It has no effect on negative 1, so it's still negative 1. Then I subtract from that whatever the limit of this is. So that's what this is written here. Then I'm going to do the same thing here. Pass through the limit. Limit t goes to positive infinity this time. E to the t times t minus 1. And then what am I going to put out here? Plus 1. And the minus 1, the plus 1 cancel, don't they? So we just have to figure out what these two limits are. If we can figure out these limits, we're done. Let's do this one first, because I think this one is a little bit easier to do. T is going to become an unbounded positive number, so it's just going to get huge. What does e do as you let the exponent become a positive, huge positive number? It becomes huge and positive also, right? It's going to be infinite. So what you have here is this is approaching infinity times, and then inside the parentheses, you have an infinitely large number, positive number, right? Minus 1 is still an infinitely large positive number. This is infinity times infinity. That is not an indeterminate form. That is something that's, you just look at it, you know what's happening. Big positive times big positive, that's big positive. So this is becoming infinite, isn't it? So at this point right here, we would say what? It's divergent. That's the answer to the question. It's divergent. Because if you go back to the notes, it says that this integral will converge, right? If you split it up, the only way it can converge is if both of these converge. Both of these would have to converge, meaning go to a number. We said infinity is not really a number. So this one being divergent, not convergent, means that the whole thing is divergent. However, I'm just going to show you the little bit of trouble you might run into with something like this. Like, let's say you had done this one first. Then you wouldn't have known it was divergent yet. What happens here as you let t become an infinitely large negative number? So what is e to a huge negative number? It's getting closer to 0, because it's the same as like 1 over a big number. Right? Because essentially you're raising e to a negative power, and that means 1 over it. So this is really approaching 0, and this one is approaching what? Negative infinity minus 1 is still negative infinity. And when you multiply 0, something that's approaching 0 times something that's getting really big, you cannot tell which one wins. So you have to do something with this. All right? Understand? So how would we do it? I just want to make sure, because I know this is definitely going to be on a test where you're going to need to know how to apply L'Hopital's rule to something like this. I'm just going to take that piece right here. I'm going to rewrite it. Watch how I rewrite this, though. This is just going to make my math a little bit easier. Is this the same as this? I'm going to a negative number, right? So when I plug in up here, t is negative. Well, instead, I'm going to let t go to positive infinity and replace t up here with negative t. So that way it still goes to a negative number. I'm going to replace this t with negative t. So you see I switched the sign. I'm going to positive infinity, but I switched the signs on t's. Okay, now the reason why I did that is so I can rewrite this a little easier, or a little bit nicer. I'm going to go negative t minus 1 over e to the t. So this is just algebra. I'm dropping the e to the negative t down to the denominator. And this is the standard technique that we use whenever we have something of this form, 0 times infinity. We always try and make a fraction out of it. And the reason why is because see what happens now. What happens if I let t go to infinity? Up top, what do we get? Negative infinity. And on the bottom, what do you get? E to the infinity this time is infinity. So you get negative infinity over infinity. And because we have an infinity over infinity, we can use L'Hopital's rule. So this tells us we can use this rule. I think that's where the apostrophe is. All right. So what is L'Hopital's rule? What does it say we do? Take the derivative of the top and bottom separately, right? And then some books will put an H here, and some of them will circle it, and some books will put an L, and some of them will circle it. In some way, shape, or form, you have to let people know you're applying L'Hopital's rule. So whichever way you want to let people know. And then just take the derivative of the top, which is negative 1 with respect to t. Derivative of the bottom, which is itself, e to the t. Right, we're not using quotient rule. This is derivative top and bottom separately. It's the only time you can do it. And now you'll apply the limit again. And now this time your numerator is fixed, right? It's not going anywhere. Your denominator is becoming infinite. And whenever that happens, it goes to 0. So the answer is still that this diverges. But had you done that first integral first, you wouldn't know that. You're not going to know it until you do this second one. That's right. 0 is a fixed number, so it's headed to somewhere. And we could even take a look at this. You know, if we graph it, just trying to keep in mind what we're doing here. Let's see. So here's the graph of this function x e to the x. And I'm only graphing it between negative 10 and 10. And if I widen this out, whoa, that's a little too much, I think. I think I went too far. Can you tell that on the right side, if I was looking for the area underneath this, it's headed off to infinity, so it's going to become infinite? But look at the left side. Yeah. It's kind of hard to see this, but on the left side, it's going down, and then it goes back towards 0. It's asymptotic, approaching the x-axis. So the area to the left of 0 is going to be a finite number. We got 0, didn't we? Oh, no, sorry. We didn't. We did get 0, but remember, if we had been looking at this left side only, there's the left integral, right? We would have had negative 1, right? Negative 1, and then this would have gone to 0, so it would have converged to negative 1, right? We canceled the ones out to start the problem, to start this out. So The area would have been -1, which you can tell from the picture it was below the x-axis, so it kind of makes sense. All right, that's it for that. Let's get back to what's next. All right, this is a nice formula to know, to remember, to have stored in the memory banks. I guess you only have one memory bank. If you have the integral, and this is very important, it has to go from 1 to infinity. All right, 1 to infinity. Of 1 over x to a power. So we call this, we call instead of n, we use p for power, I guess. If we want to know this, we'd have to set it up and do a limit, right? Well, it's already been shown, and I'm not going to show it in class. Usually I would show why this formula is true, but to save on time, I'm not going to. We just need to remember that if the number up there, the power, is less than or equal to 1, this will diverge. If the power is greater than 1, it will converge. And I believe I did an example of these right here. Integral, we've got from 1 to infinity of 1 over x to the p. Here p would be what? 2. If p is bigger than 1, it converged. And you can go back in our notes, it did converge. And then for this one, it's 1 over x to the first power. There p is 1. And so this says that if p is less than or equal to 1, it diverges. So what if you had something like this? Integral 1 to infinity 1 over square root of x dx. Would this converge or diverge? It would diverge because p is what? 1/2, right? Square root is 1/2 power. So this would diverge. Curious to see, what about this? What do you think? Think converge? Now it doesn't go from 1 to infinity. Do you think that that has an effect on the answer? This graph looks something like this. What is its value at 3? Well, 3 to the 8th power, whatever that is, 1 over that. It's a very small number. So it would be a very small number. And then as you go to the right, it gets smaller. Right? And we're trying to find the area under there. Understand? Now, if that 3 had been a what? 1, our formula would work. Correct? But plugging 1 in, wouldn't we just be like up here and we would be including this area also? So if this blue area and continuing out forever converges, then the yellow one should, right? The yellow area is less than that. So it should also converge. So that does not play a role. The fact that that was a 1 here does not play a role in this. You could have made this a 30, a 3,000, doesn't matter. Yes? Well, there is no convergent point, so to speak. It's the fact that it converges means that it goes to a finite number, right? It goes to some number. Think about if the area starting at 1 forever is finite, right? The whole area from 1 forever is finite. Then you can go anywhere and go from there on, and that's still finite because you're just taking out something from it. Does that make sense? Now, it only works on, we're only talking about 1 over x to the p. We're not talking about some general other function. Because if you have another function that goes up and down, then you do have to account for that positive and negative area, and then you could go out far enough and mess things up. So, okay, so just remember that formula. It'll be useful to us later to not have to actually compute it. We'll just say, oh, it converges, we're done. All right, and that brings us to the next type of improper integral, which are called infinite integrands or discontinuous integrands. So we're going back now. We're going to evaluate an integral from a to b. So we're not doing infinite limits of integration anymore. But we have a discontinuity at A. Now remember, discontinuities in functions were like vertical asymptotes, things like that. So let's take a look at this picture. So can you see in this picture, if I let my interval go from 2 to 5, right? I'm trying to find the area here. We have a vertical asymptote, so this function takes off up to infinity. And so there's little tiny, infinitesimally small little bits of area in there, isn't there? And I can never actually get to 2 because my function is undefined at 2. But can we still find the area? And that's what this is about, right? This is the same sort of principle as it was going out that way. Except that, do you see that now our limits of integration are finite? And the infinite part of this is coming from within the integral itself. Inside that interval is where it becomes infinite, not at the limits of integration. What about if we try and do an integral from A to B, but this time we have a discontinuity at the right side? So we have something like this, where we go -1 to 2, but at 2 it's undefined. Can we still get the area here? Right, and we'll be able to. At least we'll be able to see. It's going to be the same thing. It's either going to converge or diverge. We'll have to determine it. And then you could have this case. What if you have a discontinuity within the interval, inside of it? So here you're trying to do the antiderivative the integral from 1 to 3, but you have a discontinuity at 2. So your function's blowing up at 2. Can we find this area? This is the most tricky kind, because you have to realize that there's a discontinuity in there. And if you overlook that and you just say, oh no, there's everything in the inside's fine, there's no discontinuity, then if you just set it up like normal and just evaluate the 2 endpoints, it's completely wrong. So we have to be very careful with something like this. All of the above cases are considered to be type 2 infinite integrands. Do you see why they call it infinite integrands? The integrand is the thing that's inside, right? The function. That's the thing that's becoming infinite. The function itself is becoming infinite somewhere. So that's different than infinite limits of integration, where the endpoints are going forever. All right, so here's the definition. If a function f is continuous on this, we call this a half open or half closed interval AB. Notice that B, the function is not defined at B. That's because I have a parenthesis there, not a bracket. And we have a discontinuity at B. Then the area from A to B, look at what we're going to do. We're going to take the limit as t approaches B with what? What is this? From the left side of the integral from A to t of the function. So all we're doing is like we did before. We're replacing that limit, that upper limit, with t, and we're letting t approach the discontinuity from one side. In this case, because the discontinuity occurs at 2, we have to approach it from the left side. So we're approaching 2 from the left, not from the right. That's if the discontinuity is on the right endpoint of the interval. What about if our discontinuity is on the left side? Well, same sort of thing. This time we replace the A with T, and we approach A from the right. So here's A. We're going to have to come in from the right because our interval starts at A, ends at B. We can only come in from the right. These limits must exist and yield a finite number in order for it to be convergent. If we get infinity or something crazy, then we just say it's divergent. All these notes are online, right? Yes? Okay. All right. Now, what if you have a discontinuity from the inside, on the inside of the interval? What do you think you're going to have to do? 2 of them. right? You're going to have to break it up into two. You're going to have to, if your discontinuity is happening on the inside, we call it, let's say this is A, this is B, this is C, then what we're going to do is we're going to do this piece first, which is going to be an integral with the discontinuity on the right endpoint, because the discontinuity is at 2 on the right. And then we're going to do another integral where we go from 2 to 3, or C to B, and this time the discontinuity is on the left side. So we set the two up, we add the two together, we get an answer. Take a look at this one. By the way, while we're looking at this, if this was 1 to infinity, 1 to infinity, would this converge or diverge? It would converge, right? Because of what I just showed you, the 1 over x to the p, if p was greater than 1, it converged. If it was going from 1 to infinity, but it's not. It's going from 0 to 1. So there's some subtleties here. I'm giving you the graph, okay? But let's act like the graph wasn't there. When you're looking at this integral, you have to know where the discontinuity is. So you take a look at the denominator real quick and you say, hey, can that ever be 0? Obviously it can, right? Where's the discontinuity occur? It's discontinuous. Oh, are you contagious? Oh, great. Thank you. Appreciate that. I hope not. Or at least I hope the incubation period, is that what it's called? Is long enough to get us through 4th of July weekend, so we're not all sick. It's discontinuous at x equals 0. And 0 is one of my endpoints, right? So I have to consider it. Also, if this were from -1 to 1, right, the discontinuity would be within that interval. So what I like to do is I like to just draw a number line. I like to draw my two endpoints that I'm interested in, right? That's the endpoints of my integral here. And then I'm going to somehow let myself know that at 0 is where I have a discontinuity, right? Just going to say discont. My discontinuity is right there. That means that I have some sort of asymptote here, which means that I need to somehow approach that value from which side? Right side. See, it doesn't make sense coming from the left because I'm looking just between 0 and 1, so I must come in from the right side. So to do this, I'm going to set up a limit. I'm going to let t approach what number? 0 from the right, so a little plus sign on it. And what is it that I'm replacing here in my integral? The lower limit of integration becomes my t. Upper limit of integration still stays as 1 because I don't have any problems, right, at at 1. What is the antiderivative of this? -1 over x. So I've taken my antiderivative now, -1 over x, and I'm going to evaluate that from t to 1. Plug in 1 first. Still have a limit out here. Okay, I've got 2 sets of parentheses. You plug in 1, what do you get? Just -1. And then when you plug in t, you get -1 over t. I'm just going to clean this up a little bit. Negative 1 plus 1 over t. We probably could have been able to resolve this a long time ago, but I just want to write everything down. Any questions on any of this? What happens when t goes to 0? One over 0, which does what? We're drawing back on Cal 1. What happens when the numerator is fixed, it doesn't move, and the denominator heads towards 0? What does it become? Yep, there were three possibilities. I don't know if you remember this from Cal 1. It was either infinity, negative infinity, or the limit wouldn't exist at all. Does not exist. That says DNE. To determine which one of these it is, you just look at the signs of what's going on. 1 is a positive number, right? So it's a fixed positive number here. Your denominator is headed towards 0, but we're headed from the right side of 0, which means that we're headed towards 0 through positive numbers, right? Look at our number line. We're headed towards 0 through positive numbers only. And since the positive numbers only, I'm headed towards 0, I'll put a little plus sign, from the right, so that those are little positive numbers. Now we know the ratio is getting huge, right? The bottom is getting smaller, the ratio gets big, but they're always positive numbers. So your answer must be positive infinity. The importance of this approaching from the right is that if you did not approach from the right, then what would this limit be? Does not exist. The limit would not exist. Because from one side it would be one thing and from the other side it would be something else. And so the limit wouldn't exist. Now at the end of the day for this problem, it's not going to matter which one of these it was, because in all of the three cases we would get what? That this is divergent. Right? Because this thing becomes infinite, and then of course negative 1 plus infinity is going to be headed towards infinity, right? Which means that the integral is divergent. That's the opposite of what it just did the other way, right? From when we went out the right side forever, it converged. That area was finite, but if we try and pick up the area between 0 and 1, it's infinite. Any questions? Yes. Yep. Okay, if this wasn't a plus, okay, if this right here was not a plus, then remember that if you take a limit of something and there's not a plus or a minus, you have to approach from both sides. You would have to approach 0 from both sides. So let's say I come in and I approach 0 from the right first. I would get positive on top, positive on bottom. That would be positive infinity. Then if I approach 0 from the left side through negative numbers, I would get a fixed positive number over a tiny negative number, which would become a huge negative number. So you basically just look at the graph of 1 over t. It looks like this. So as you come in from the right, it goes to infinity. You go from the left, it goes to negative infinity. And so from both sides, they're going to different places, so you would get does not exist. It would not change the divergence of it, but it would still be a different result for the limit. Divergent or convergent? Yes. At the end of it all, that's what we want. Yes. And if it's convergent, we're actually figuring out what it converges to, as the next example will illustrate. So take a look at this one. I'm not going to show you the picture yet. So we're so used to now looking at integrals and just being like, okay, I need to just find the antiderivative. I just need to do that. Once I do that, I plug in the endpoints, I'm done. But now we have this new added element that we always have to be careful that the integrand itself is not discontinuous somewhere. So take a look at this thing. Is there something that would cause the denominator to become 0? What number could I plug in there that would make that thing messed up? 2, right? 2. 2 is going to cause a problem. So I have a discontinuity at x equals 2. And it just so happens that the interval I'm looking at goes from 0 to 2. So I have a discontinuity right there. That means I have to approach 2, right? I have to try and approach 2 from which side? Left side this time. What's today? 7. Everyone understand it? Like physically what's happening in the number line, which side we're approaching 2 from? All right, so this time I'm going to replace the 2 with t. I'm going to set up a limit. I'm going to let t approach 2 from the left. So limit t approaches 2 from the left. I put a little negative to the top right of it. Integral 0 to t, 1 over square root 2 minus x dx. Now I have to find the antiderivative. Any ideas on that antiderivative? Basic u sub? Okay, let's do a basic u sub. What's your u going to be? 2 minus x. 2 minus x, the derivative of that is negative dx. So I'm going to be able to replace this with u. And then I need a negative dx. I don't have a negative dx, but I can just multiply both sides by negative 1, which will change that to a negative and this to a positive. So that means I'll replace dx with negative du. Now I'm going to do that over here. I'm not going to put it over here, all right? I don't want to rewrite my integral in terms of u, because if I do that, then I need to change my limits of integration also, because these limits are the values of x, not u. And there's kind of two schools of thought. Some instructors focus on if you're going to change your integral to u, then you have to change your limits of integration. I've always been in the school of thought of change it to u, get your antiderivative, change it back to x, and just use your limits. Don't worry about an intermediate step of trying to convert these over. So rewrite this integral over here. It becomes what? Negative 1 over square root of u du. Do you feel bad? Do you feel like you have a... Okay. You're kind of worrying me a little bit right now. Oh, okay. My wife's been sick for almost 2 weeks right now. She cannot get over this bug, and I just don't want it. Whatever it is, I don't want it. So, all right. So u to the negative half, and what's that antiderivative? And when that's all said and done, negative, is it negative? 2 u to the half plus c. This is all stuff you should be able to do by now, right? But do y'all agree or not? Y'all are looking at me like I've messed something up here. All right, I'm going to replace u with 2 minus x. So negative 2 square root 2 minus x plus c. So this was all my work on the side just to get my antiderivative. And now I can come back in here and I can set up this limit and have my evaluation take place. So this is limit t approaches 2 from the left side of the antiderivative, which was negative 2 root 2 minus x. I'm going to evaluate that 0 to t. Let's plug in t, then plug in 0. So 2 sets of parentheses here. When I plug t in, I just get the expression itself with the x substituted out for t. And when I plug in 0, what do I get? Negative 2 root 2. That's okay. That's a number. That's fine. And now let's let t approach 2 from the left side. That's critical, from the left side. If you need to, just draw a quick little number line over here. Remember what it means. You're approaching 2 from the left side, coming in from the left side of 2. So give me an example of a number that's really, really close to 2 from the left side. 1.99999. All right. What's 2 take away 1.99999? Very small positive number, right? Can you take the square root of a positive number? Absolutely. But we know it's very small. So we know that 2 take away 2 is approaching 0, and it's defined. That's the key to it. Coming in from the left, being 1.9999, it's a very, very close, when you put it in here, it's very close to 0, but it's positive, which means the square root exists. Do you see that if we came in from the right, couldn't do it? Because it would be a very small negative number. So this is well defined. We plug in. This is approaching 0, which kills off everything, right? So you get, after you take the limit, okay, this whole thing vanishes out to 0, and you're left with 2 root 2. The double negative becomes positive. Right, that goes to 0. Questions? Questions? Yeah, it wouldn't make any sense. And you know what that would mean probably is that you're coming in from the wrong side. Because if you had a square root of a negative number, then you would be messing around in a place on the number line where your function didn't even exist. See, our original function doesn't exist at 2, right? But it also doesn't exist to the right of 2. Because if you try plugging in 3 here, you're going to have negative down here. So this integrand itself has a domain restriction that if you were on the outside of 2, you'd be in trouble anyway. You shouldn't have that happen, yeah. It's weird. There's a lot of really strange connections between a function and its derivative and antiderivative. If this function has a domain restriction, its derivative will have the same domain restriction, and its antiderivative will also. Now, sometimes the domain restriction on the derivatives and antiderivatives is you know, a little more endpoints change or something like that, but basically they maintain the domain restrictions throughout differentiation and integration. It's kind of nice. All right, so this one converges, but I need the answer, right? 2 root 2. So the area under that curve between on the interval 0, 2, even though there's a discontinuity there and it becomes infinite, it has a finite area. Interesting. Oh, there was the graph of it right there, just so you could see it. That's what it looked like. Okay, so I'm going to help you start this problem. I'm going to give you about 5-10 minutes to see if you can work it out. But I'm going to help you get it set up. Please be aware of the major danger now. I've pointed this out as, I think, third problem. I'm pointing it out for the third time. You do not want to just start these problems by finding antiderivatives. Find antiderivative, find antiderivative. You need to pay attention now to these limits of integration, how they affect what's happening in here, if your function's even defined in there, if you have discontinuities. So maybe start this by looking at the denominator and asking yourself if that's ever zero. That's been what we've done on these three problems, right? But if this was a trig function, you'd be looking at places where the trig function is undefined. It just depends on what's in there. Everything we've looked at has been a rational function up to this point. Well, the last one wasn't, but it's been simple to just say, oh, when is the denominator zero? Same thing here. So tell me about this. Where is this discontinuous? At 4? Is that the only place? At 0 also, yeah, good. So I wanted to make sure everyone just realized we're just setting the denominator equal to 0. We're figuring out the solutions to this quick little quadratic. We can factor an x out, x minus 4. We get two solutions, x is 0 and x is 4. Only one of these solutions matters to us because only one of them has anything to do with the interval we're looking at, right? So I'm going to chunk the 0 and just focus on the 4. My interval goes from 1 to 4, and the 4 is where I have the discontinuity, which means I'm going to need to approach it from which side? The left. Okay, so now I'll let you work 10 minutes. And, you know, work with each other if you need to. This is more just practice right now, okay? I'm going to pause my recording. So here's your partial fraction set up on this. Because it factors easily, you set up your two linear A1 and A2 on top, or your two constants on top of your two linear factors. Go through, solve for A1, A2, and you'll get negative 1/4 for A1 and positive 1/4 for A2. Then these are just simple natural logs. And so this is our antiderivative. So let me plug that back in here. This will become limit t goes to 4 from the left side of the antiderivative, which was negative 1/4 natural log of the absolute value of x plus 1/4 natural log of x minus 4 absolute value, evaluated 1 to t. I'm going to try and do this without writing the two sets of parentheses. I'm just going to see what happens. What happens when I plug in t here? I'm just going to get a t here and then t minus 4, right? Now let each of those go to 4. Approach 4 from the left side. So if I put the t here and then I replace t with 4, I'm just going to get natural log of 4, right? Absolute value, doesn't matter, natural log 4. But if I try and plug 4 in here, 4 minus 4 is going to be 0. And what's natural log of 0? Well, it's undefined, but again, this is a limit, right? We're letting t approach 4. So that means the natural log is approaching 0. But it's absolute value, which means it's approaching 0 from positive numbers. So what does natural log look like? I'm going to graph natural log over here. Here's natural log of x. It looks like this, doesn't it? And as you approach on natural log x, as you approach 0 from the right side, right, because that's what's happening when I replace that with 4, this is approaching 0. Absolute value is positive, so I'm approaching it from the positive side. And it's headed towards negative infinity, isn't it? What does that mean? This thing diverges, right? This is becoming infinite. So you have a finite number, natural log of 4 times negative 1/4, who cares, that's finite, plus this infinity thing, either positive or negative, doesn't matter. That means this diverges. Doesn't matter what I get when I plug in 1 now, does it? You could stop there. You could say something like, at this point, if you want to do it right, you would say something like, but the limit t approaches 4 from the left of even just, you don't even have to worry about the 1/4 out front. This right here, right, is negative infinity. Therefore, the integral diverges. The 3 dots means therefore, right? I think I mentioned that here, didn't I, once before? Therefore, integral diverges. All right. Questions? So you see the techniques of integration aren't going to go away. They're still going to be there. Possibly, if you use something else. All right, so this one is an example of a problem where we have a problem inside. And I shouldn't have shown you the graph first, but it's too late. All right. So let's take a look at how you do this one. So I'm taking a look at this. I'm saying, when am I going to have a problem with this? Well, cube root is never a problem because you can always take a cube root of a positive or a negative number. That doesn't matter. But you could get division by 0. And if you look at this radicand, x minus 4, if that's 0, the cube root of 0 is 0, and then division by 0 would occur. So what you want to make sure is that you're aware that there is a discontinuity at x equals 4. Now I'm going to draw my number line. I'm going to go from 3 to 5, but I have a discontinuity here at 4, right? That's my discontinuity. Which means that if I'm going to do this, I have to be able to approach 4 from the left and from the right, because my interval is on both sides instead of it being at an endpoint, which means it's going to require 2 separate integrals. One to take care of the left side, one to take care of the right. So remember how we split negative infinity to infinity up? We said negative infinity to 0 and then 0 to infinity. That's what we have to do here, except we don't get to choose the middle number. It has to be the 4. So this right here is going to become the integral from 3 to 4 of x over cube root of x minus 4 dx, plus the integral from 4 to 5 of x over the cube root of x minus 4 dx. I'll highlight where our discontinuity is. The first integral becomes a limit. I'm going to let t approach what? 4 from the left. So I'm doing this, the 3 to 4 is this integral right here, covering this. So I'm approaching 4 from the left. Of 3 to t x over cube root x minus 4 dx, plus another limit, this time as t approaches 4 from the right, integral t to 5 x over cube root x minus 4 dx. Understand the setup? Questions? We need an antiderivative. What do you got? I might do my antiderivative on another page, just so I can have more room to write. What are you going to do for this antiderivative? U sub? What's your u? X minus 4? du is dx? And x equals u plus 4. So this is one of those ones where you make a basic substitution, you replace this with u, it's going to become the cube root of u. The dx gets replaced with du, but then you have to replace the x, so you take this and solve for x. So you get integral, x on top was u plus 4, over cube root of u, which is u to the 1/3, then dx was du. And the advantage to this is that we can split this into two integrals because we have two terms on top, one on the bottom. So this is integral u over u to the 1/3 plus 4 over u to the 1/3 du. Which is integral u to the 2/3 plus 4u to the negative 1/3, bringing the u back up. And then you use power rule on each of those. Antiderivative of u to the 2/3 is 3/5 u to the 5/3. And then antiderivative of u to the 1/3 is 3/2 u to the 2/3, but then you add a 4 in front. So plus 4 times 3/2 u to the 2/3 plus c. Clean it up. What was u? X minus 4 to the 5/3 plus, let's see, you get some cancellation here. So get 6 times x minus 4 to the 2/3 plus c. There's our antiderivative. Any questions? All right, I'm going to go back to the previous page. And this will be, let me paste this thing in here first. There's my antiderivative. Just going to keep it there so I can look at it. This is going to become limit t goes to 4 from the left of the antiderivative, 3/5 x minus 4 to the 5/3 plus 6 times x minus 4 to the 2/3 evaluated from 3 to t, and then plus blah, blah, blah. That blah, blah, blah is this one, right? I'm not going to rewrite that one. I'll let you do that yourself. But it's the same thing, right? Same sort of setup. Now, let's try this again without writing the two sets of parentheses. What happens when you replace all your x's with t's and then let those t's become 4s? What happens? 4 minus 4? 0. 0. Everything goes away, right? And that's okay. We're not getting any infinities or anything like that. I don't even have to care about which side I'm coming in to 4 from, because this really means I'm taking a cube root and then raising it to the 5th power. I can take the cube root of a positive or negative number, so it doesn't matter. I don't run into any issues here. Same with this. So when I plug in t and then let t go to 4, the whole thing goes to 0. Now I have to just replace all my x's with what? 3. So let's do that. If I plug 3 in here, I get 3, what, minus 4 is negative 1. So I'll write this one down. And by the way, this was, here's what we had. We had 0 when we plugged in, then minus 3/5, -1 to the 5/3, plus 6, and then won't we get -1 again? To the 2/3, plus blah, blah. That's the other integral, which I'm not going to do. All right, what's -1 to the 5/3? What is it? -1. You take -1, you take the cube root. What's the cube root of -1? -1. What's -1 to the 5th power? -1. Or you could have done it the other way around. -1 to the 5th power, -1, and then take the cube root, still -1. So this is all -1, isn't it? So we have minus 3/5 times -1 plus 6 times, now what's this one? What's the cube root of -1? -1 squared, +1. Or you could do -1 squared, +1, cube root of +1 is 1. Either way, it's going to become a 1. Put this together here. We have minus -3/5 plus 6. Get a common denominator here. So 30/5, take away 3/5 is 27/5, and then make it negative. So -27/5 plus, I didn't do this side over here, but you get a number over there also. So this is going to converge, but I'm not finishing it off. Understand? Okay. Converges. There's the picture. All right, I'm not going to go through this one. I'll talk through it. Well, I don't know. That integration might look like trouble. Where do you have a problem here? Where do you have the issue? 0, right? I mean, again, the picture's giving it away, but you can tell from this, right? You plug 0 in, this is division by 0, but also you get 0 on top also, right? Or when you plug in 0, you get what? You get like -infinity or something. Like it's something weird's happening here. But you have a discontinuity for sure at 0, and that's your interval involves 0. How would you do the antiderivative for that? Rewrite this right here as x to the -1/2 on top. Yes, what would you choose for your u? Probably natural log. Because derivative of natural log is what? 1 over x, which was okay because the other one would be the x to the -1/2. You could go antiderivative of that, and then when you put those two together, it would just be a power of x. So integration by parts would work on that. Does a basic substitution work? I don't think so. No. Well, I'm more curious than anything else right now. We all see we could do integration by parts. I wonder if this would work though. Is that the same problem? Okay, so then this is the same. I don't know if this is going to work. I'm thinking through this. I did that to try and make the bottom look like a 1 over x. So what I really have is this. Do y'all agree that's the same problem? And now basic substitution, u is natural log of x. What's the derivative? 1 over x dx. And I have 1 over x dx. I've got it. I've got natural log x. I just need to figure out what the square root of x is. That wouldn't be so easy, would it? So I don't think I'm going to be able to save myself. I might be able to manipulate this, like e to the u equals e to the natural log x. Why would I do that? Because that's this, right? And then you would take the square root on both sides. The square root of the left side is the same as raising it to what power? 1/2? So do you agree I could replace it with this? I mean, if you follow this? And isn't something to a power the same as this? U to the, you multiply the power? Like that? I don't know if I made it easier or harder here. So I'm going to replace square root of x with e to the 1/2 u. Natural log of x is being replaced with u, and then 1 over x dx is du. Oh, and guess how I would do this? Integration by parts. So I don't think I did anything but made it look different. I still have to do the integration by parts. So I was just curious if that would go any easier, but it doesn't look like it does. So, all right, oh well. Okay, that's it. So what, did I give you homework out of that section last time? I did. 6-6, right? What did I give you last time? Did you say yes I did or no? 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 Page 360? I thought I did, but oh well. If I didn't, that's okay. Oh, okay. I was asking you to go practice the definite. 5 through 31 odds. That's a good mixture. The first, let's say, first about 9, about 8 or 9 of them are all the first type, and then the rest are the ones we just did right now, type 2. All right, we are going to move on. We're going to get into Chapter 7 now. Chapter 7 is titled Applications of Integration. All right, so we're gonna start looking at applications of integration, you know, where we can use this. And I mean, there's a bunch of different things we can do, but the first application is very geometric. And it's kind of how we started looking at integration when we started doing definite integrals, the whole idea of an area under a curve. But now we're going to look at the area between curves. So now you may have more than one curve. You may have a function, another function, you're trying to find the area between the two. So I'm going to come up with a formula here for us, and I want you to keep in mind that we are using vertical rectangles, and the curves we are looking at are functions of x. Now, that may not make a whole lot of sense right now until I start showing you the picture, but just keep in mind when you refer back to these notes, this is the situation we have. Suppose you're given two functions, f of x and g of x, with f of x greater than g of x on some interval a, b. So you have your function f is above the function g on some interval. Then the area between the curves is given by this integral. which I think makes perfect sense, hopefully to you, that this formula would work. What would if I took the minus g of x out completely, what would that be? If the integral a to b of f of x dx, what would that be? Area just under f all the way down to where? The x-axis, right? And then I'm supposed to come in and take away this integral. So what's the area with from a the integral from a to b of just g of x? That'd be the area under g to the x-axis. So if you take the area under f to the x-axis, take away the part from g to the x-axis, you should get the remaining area between them. So I think you see the picture, but you never know. I think a lot of things sometimes, and I'm wrong. So this area right here, the whole thing, that would be the integral of f, wouldn't it? This area, the blue, would be the integral, the area under g, right? And so if you take the yellow and you take away that light blue, you get the area between them. So that's how the formula works. But I want you to look at this a little bit different, okay? Just a little bit different, and this will help us as we move forward. I want that area, right? So remember how we did areas with Riemann sums? We did rectangles, didn't we? So imagine coming in here and just taking an arbitrary rectangle, like this. And over here on the side, I'm going to draw it again. Terrible, terrible, terrible. I'm also going to label the x-axis here, right? So I'm just taking this picture to the side, and I want the area of that little rectangle. Well, we know the width of it. How wide is this thing? Didn't we call that dx? Wasn't that our delta x, which was b minus a over n? That was our delta x, but we let it go to infinity, number of them go to infinity. So this turned into our dx in our formula. Now, how tall is this rectangle? Well, we have two functions. We have a function that came in on top, and we had a function that's coming in on the bottom, right? The top function is f. The bottom function is g. So I'm trying to find the distance from here to here, which should be, this distance should be the f function's height, take away the g function's height. Do you agree? Total height from the x-axis all the way to the top, that's f, take away from the x-axis to g. That should be the height of that rectangle, right? So the area of that one little rectangle, the area of that, I'll say the area A, equals f of x minus g of x times delta x. That's the area of just this guy right here. Now I want all the areas, don't I? I want to add them all up. So anytime we want to add them up, make an infinite number of them, we do a sum, and when we do an infinite number, the sum becomes an integral, right? So the formula is going to be the integral, which means, hey, I'm going to add up all these rectangles, an infinite number of them. The area of each rectangle is the f of x minus the g of x dx. And I'm going to start out at A and end at B. Right? I'm going to start at A and end at B. So do you see how this formula, you can get this formula from this geometry instead of me just saying, hey, here's the formula. Does it make sense? You can get it from the picture. And that's going to be very useful in a second when we start rotating these things around axes and getting volumes. Questions? Also, one other thing that'll become useful later. The distance from here to here. So imagine we had to pick a rectangle in there, right? I just picked an arbitrary black rectangle sitting in there. I could have picked this one that sits here, and the formula would have been the same, wouldn't it have been the same for that? Where we pick the rectangle, right? Where we pick has to be between A and B, but it's arbitrary. So we call this X. X is like the distance out. Now that did not contribute at all to this formula, all right? It didn't matter where we were as long as we're between A and B. But again, in a little while, that distance we go to the right is going to matter. All right, questions? Everyone got the formula, understand where it comes from? So now, what if we have a different situation where instead of having functions of X, you now have functions of Y? So remember, function of X means it passes the vertical line test. Function of Y means it passes the horizontal line test but fails the vertical. Or you could have both. It could be both a function of X and Y. It could work both ways. But look at this picture right here. Do you see in this scenario, the red function here is, or the red curve, is not a function of X. It fails the vertical line test, doesn't it? So you cannot write the red function as a function of X. But if you look at it sideways, right, turning your head 90 degrees and applying a vertical line test that way, then it would be, correct? So one thing that I'll point out, because we will be doing this quite a bit, when we look at a graph like this, up to us is positive, right? Down is negative. Up is positive, down is negative. If we turn our heads 90 degrees, when I say 90 degrees, I'm saying clockwise 90 degrees, and we look at that, then up is positive and down is negative, isn't it? Let's just make sure we understand that when we're talking about visualizing this graph from a different perspective, that we want to turn our heads this way so that up is this way, or top is here and bottom is there. Got it? All right. All right, so I'm going to take this, and I want to try and again come up with the formula for this. I'm pretty sure you probably see it, but let's practice this again. So I'm going to take an arbitrary rectangle. Because these are functions of y, I'm going to call the red one f of y, and I'm going to call the blue one g of y. Why am I labeling it that way? Why not do g on the red one and f on the... Yeah, because we want it to follow the same format. In the previous one, the f was on top and the g was on bottom. I want the f to be on top and the g to be on bottom here. So when you turn your head to the right, the red one's on top, that's going to be f. The blue one's on the bottom, that's g. With me? Now what we're going to draw are a horizontal rectangle instead of a vertical one. Before I draw it, do you see why I could not draw this and I couldn't do it this way? Do you see why I can't do that? We'll ask, what's his name? I'm not sure. I don't want to disturb that. It looks peaceful. Hey, all right. You want an opportunity to explain why we can't do the vertical rectangle that way? I'll zoom it in. Remember, the rectangle is arbitrary, isn't it? I could do a rectangle here also. Would this rectangle be okay? Could I somehow define it, this rectangle, the height of it? Could I do that? This one would be okay, right? Because look, the blue one would be on top and the red one would be on bottom, right? So I would have like a height difference, but why not here? the top is also the bottom. It's the same curve. You see why I can't do vertical rectangles here? The top and bottom have to be different functions for me to be able to do a difference and it makes sense. That's why a vertical rectangle will not work here. This is why we must view these as functions of y. Instead, when you view them as functions of y, you have to turn your head sideways and draw your rectangles horizontally instead. So now draw a horizontal rectangle like this. And imagine I move that rectangle, slide it up and down in that shaded region. Is it going to always be the red one on top of the blue one? Yes, right? No matter where you put it. Right? So I must use those. Now take this thing to the side. I'm going to take that for the one I drew on top over there. Okay? Take that one. I'm going to take it to the side. I'm going to draw it again. This time, since I'm going sideways, I'm going to draw the y-axis. Do I know the little tiny height of that rectangle? I'm going to call this the width this way. What's the height of that rectangle? The change in y this time, right? It's not delta x, it's delta y. So we'll call that dy. Is that right? In the infinitesimal, meaning when we go really, really narrow rectangles, that's dy. And then I have my two curves. I have the red curve coming in, and I have the blue curve coming in like this. Well, it's not a curved straight line. This is my g of y. This one is my f of y. So how wide is this? Distance from here to here, right? So what's the difference all the way from the y-axis all the way up to the red? That's f of y, and then distance from the y-axis to the blue is g of y, so distance from here to here would be the difference between the two. And we get the same formula that we just had, except in terms of y instead of x, don't we? So the area of one of those pieces is this length times dy. That's the area of one piece, and we want to add them all up. So we're going to go integral f of y minus g of y dy. Now here's a little bit of a difference also. We initially went A to B on the previous problem. That was our left and right points. I didn't label those, did I? I should have labeled them. There we go. A and B on this one would have been this left end point and this right end point, right? That would have been our A and B. Here, we are not using that. What are we using? We have a point here, and we're using the y coordinate, and a point here, and we're using the y coordinate here. See, we're not using x coordinates because everything's in terms of y, so we have to use y coordinates. And instead of A to B, we use two different letters. We use C to D for whenever we're doing our integrals this way. So C to D. And notice that C is the one on the bottom and D is the one on top. Because negative is down, positive is up, right? So we will go C to D. So that's your formula. Are there any questions? All right, so that's what this formula is saying right here, except I didn't label what C and D were. On the previous one, I had not labeled what A and B were. All right, this one, I'm just going to give you the problem. I'm not going to give you the picture, because on a test, you're not going to be given a picture. So we'll take a break after this problem. Sketch the region bounded by these two curves, then find the area of the region. All right, so we are going to start to need to be able to sketch stuff. I encourage you to use a graphing calculator, but I hope that you would not be dependent upon a graphing calculator for something like this. But if you have one, and you know how to use it, then you may as well, get your money's worth. I'm just going to throw some grid paper up here just to make it a little easier for myself. Let me sketch these two first. Y equals 2 minus x squared. That's a parabola, right? It opens down. It has a y-intercept of 2. I might have to make several sketches. I'm going to exaggerate this. This is 1. This is 2. 1, 2, -1, -2. So when I draw this parabola, I need to start at y is 2, and then it's going to go down, right? Where does it hit the x-axis? Well, you'd have to set this equal to 0, wouldn't you? And you would get two solutions, √2 and -√2, which is about 1.414 and -1.414. So again, this is kind of a quick sketch. We want to get an idea of what's happening. It doesn't have to be perfect. But that would be, I guess, good enough. Oh, wow. It's supposed to somewhat look symmetric. Gosh. Okay, there we go. I'm happy with that. And then y equals -x. What does this look like? Or diagonal, slope -1. So I'll draw this one in blue. Looks like this. It's supposed to be straight. I think that's enough information for me to figure out the region bounded by the 2, right? Can you see the region that's bounded by the 2? It's this in here. And I need to find the area of that. So the question now is on you. Are you going to do vertical rectangles where these are functions of x, or are you going to do horizontal rectangles where these are functions of y? So which one do you think? Vertical? Why? Horizontal wouldn't work all the time, right? Like if I tried to draw a horizontal one up here, that would not work because I would have the same curve for top and bottom, well, left and right, top, bottom. That wouldn't work. But if I draw a vertical rectangle, it doesn't matter where I place that vertical rectangle, right? It doesn't matter where it is. If I slide this within the yellow left and right, the red one is always on top, the blue one is always on the bottom, isn't it? No matter what. So let's just identify my red one. I'm going to call that f of x because it's the one on top. And which function was that? 2 minus x squared, okay. And then the one on the bottom, g of x, was equal to -x, wasn't it? Okay. Some people are really particular about this, like label your x-axis, label your y-axis. I'm not so much, but if you want to get better at this. Now, to the side, I'm going to draw my rectangle again. Why? Because I'm practicing for later, all right? I'm going to draw my rectangle over here. My x-axis actually comes through it. But if I would have slid this rectangle up here, then the x-axis would be below it, wouldn't it? But that's the way I drew it, so I'm going to go with that. And from that, tell me about, see, the red one comes in on top like this. The blue one comes in on the bottom like this. So that allows me to determine that this will always be the f of x minus the g of x. The width of this was dx. And what is f of x minus g of x? I don't have room here. Isn't that 2 minus x squared? That's f of x. And then take away what was g of x? Negative x. So you're taking away a negative, which means you have 2 minus x squared plus x. This is going to be the integrand, isn't it? This is the integrand. This dx is the dx. But geometrically, that's the width and well, this is the width and this is the height. What's missing still? What do we need? We need the limits of integration. We need where to start and stop, which we hadn't had to do before. So I need to figure out these 2 points, don't I? Highlighting them in blue. Those are the intersections of these 2 curves, right? How do you find the intersection of 2 curves? Set them equal to each other. So that's what I'm going to have to do. So this is going to be kind of an additional step that we'll have to do most of the time. Okay, the intersection of f and g. That's what I'm doing now. So I take f, I set it equal to g. What type of equation is that? It's quadratic. Move everything to one side. I'm going to move everything to the right. I solve that quadratic equation by any method I can solve it with. Always having quadratic formula if everything else fails, but it factors because it's our first example. And you get 2 solutions, 2 and negative 1. And let's just verify, looking back at our picture, do these actually look right? Negative 1, yes, that looks like where they hit. And then 2, well, my picture's not that great, but I feel comfortable with it. Understand? If you graph these on a calculator, you can even have your calculator find the intersections for you. But I'm going to want to see the work. I'm going to want to see the setting up of the equation, the solving. All right, what's the integral? Let's set it all up, write down what we're going to have to evaluate. Integral from negative 1 to 2 of, what was it? It was 2 minus x squared plus x dx. And that equals, who knows what, dot, dot, dot. You could figure that out on your own. Right? Power rule on each of those. Plug in the endpoints, you're done. Okay, I think this is a good point to stop. We'll resume at 11. Okay, so just a little bit of info on the types of problems that you'd see on a test. For this next test, a lot of the problems are going to be sketch the region, set up the integral, do not evaluate the integral. So it'll be just the setup of it and the drawing that's graded. And then whatever integral you set up, you can write that down on a separate piece of paper, take it home and evaluate it and bring it back, and that'll count as like an extra or bonus or something. Because they're too time consuming. We don't have a lot of time on the test to evaluate each integral. Some of them get pretty nasty. So, okay, how about this one? Oh, there was the picture to confirm what we had. How about this one? Sketch the region bounded by these 2 guys there. Come on. Actually, not, I said these 2 guys. It's not. So sketch the region bounded by y equals square root of x, y equals x minus 2, y equals 0. So there's actually 3 curves given to us. So we need to draw all of them to make sure we have an understanding of what region we are referencing here. So y equals the square root of x. I know that that looks something like this. Y equals x minus 2 is a line, slope is 1, y-intercept is negative 2. So it looks something like that. Okay, if that were it, would I have an enclosed region? I wouldn't, right? I mean, you couldn't say it was this because that x-axis doesn't stop anything. It's almost like, have you ever used that fill function on a computer, like Paint program, where you fill, if you were to try and fill this right here, it would just fill everything because there's nothing stopping it. So it's not that. So that's why we need that last piece of information, y equals 0. Y equals 0 is the x-axis. So I come in here and I fill in y equals 0 right there. And now that definitely encloses this region right in here. So I'm going to come in here and determine if I'm going to use vertical rectangles or horizontal rectangles. What do you think? Could I use vertical? If I did a vertical rectangle here, do I have a function on top and on bottom? The red one's on top, the green one's on the bottom, yes? But when I get over here, it's switched now. It's the red one on top and the blue one on the bottom, isn't it? So if you're going to do vertical rectangles, what you would have to do is split, those are supposed to be, it's dotted line. You'd have to actually split it into 2 integrals. The first integral would go from wherever this is to wherever that is, and it would be the red one minus the green one. Then you would have to go from this point of intersection to this point of intersection, and there it would be the red one minus the blue one. So it could be done. Do y'all see that? It could be done with vertical rectangles. But it's more efficient to do with horizontal rectangles because you only have to set 1 integral up. Let's just see how that would work. Oh, wonderful. It's not at all what I wanted to do. Yeah, I know. Screw it. I can't do it. There, okay. All right, so if I come in here with horizontal rectangles instead, horizontal would look like this. And notice that even if I move it up or if I move it all the way to the bottom, it's always going to be looking at it sideways, right? How do y'all want to do this? Every class is different. Would y'all rather me say, turning our head, we have a top and a bottom, or would you rather me just say right and left? Do y'all care? Turn your head? Okay, we're going to do it that way, right? Do y'all see it? That the horizontal works better. So if I'm going to do this with horizontal rectangles, then I need to rewrite all of these curves as functions of y. So let's look at the first one here. Let's see the red one. Right now, it's solved for y. So I would say f of x is the square root of x. But I don't want it to be that. I want it to be a function of y instead. So I need to solve it for x. So how do you solve that for x? Square both sides, right? Also, there's one other condition. Y must be greater than or equal to 0. In other words, this right, sorry, this is not right. What should I have put? Sorry. Y squared equals X. And I want the Y to be greater than 0 or equal to. And that's because Y equals, or X equals Y squared is a parabola that opens sideways, but I don't want the bottom half. So to draw this picture, it's this parabola, but just the top part of it, the positive part of it. All right, I need to take this next one, which is the blue line. I need to solve it for X. So that would be what? Y plus 2. That one's an easy one. And then what about Y equals 0? I can't solve that for X, can I? But that's okay because this line right here is not a function of Y. All that's going to give me is one of my endpoints for my limit of integration. That's all that's going to help me with. Understand? So let's call this red one f of y equals y squared. No. F is the top one. Sorry. F of y is y plus 2. So when you turn your head and you look at this, the top one is the blue one. So that's why I'm calling it F. And then that means the red one, I'm calling g of y is the one on the bottom when I turn my head. And that's your y squared. Y'all with me? All right, now below this, I'm going to zoom out a little. I'm going to draw my little rectangle down here. Here's my y-axis. I have the red one coming in on the bottom. I have my blue one coming in on the top. So this distance here is f of y minus g of y, which for us is y plus 2 minus y squared. And what's the little infinitesimal height of it? dy, right? But all we really need to do is pick this piece up, right? Just pick that up. That gives us the integrand. So I think I've got the integrand. I'm ready to set up the integral. I need my limits of integration. So where am I going to look for my limits of integration at? Where are they going to come from? Will they be x values or y values? Y values, because I'm integrating with respect to y. So how about where the blue and the red hit up here? Right? I need the y coordinate, not the x coordinate. I'm not looking for this point. I'm looking for the y coordinate where they hit. And then also I need this left endpoint, but that left endpoint is actually that line, and that's just y equals 0. So one of them I have, the other one I have to find the intersection. Are there any questions? What am I going to set equal to each other in order to find the intersection? The y squared must be equal to the y plus 2. So setting the blue and red ones equal to each other, because that's the two I'm interested where they hit. So I'm setting y plus 2 equal to y squared. That's a quadratic again. Y squared minus y minus 2. We get two solutions, right? Y minus 2, y, is it plus 1? What are our two solutions here? 2 and negative 1. Now, does that mean my integral is going to go from negative 1 to 2? No. See, what's happening is that that intersection that we solve for does not realize that we've cut off the bottom half, so it's trying to pick up the intersection on the other side. So when I said up here y had to be greater than or equal to 0, that's what helps me remember I chunked that answer. That's not going to be a valid answer. So I'm ready here it is. Integral is going to go from 0 to y coordinate of 2 of the difference of the two functions, y plus 2 minus y squared, all of that dy equals dot, 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 dot. So on a test, this is what I'd be looking for. Now, on a problem like this, I might ask you to actually find the area, because that's not going to take that long. But as these get more complicated, it might take longer. What's that? 10/3? Okay, comes out to be 10/3. All right, let's see what's next. There's my picture. Is that the same problem? So that's probably to show that you could set it up, unless I just repeated it. No? Are they exactly the same? Yeah. Well, remember I said you could do it two different ways, right? So you could try it the other way, but I mean, why waste your time doing two integrals when you can just do one, right? All right, here's one that's a little more interesting. Sketch the region bounded by y equals sine x, y equals x equals pi over 2, x equals pi, and then find the area of the region. So you need to know how to sketch the sine function. I know sine looks like this. If I say this is 1 up here, -1 down here, I know sine has a period of what, 2 pi? 1, 2, 3, 4, 5, 6. So sine looks like this. Goes up, comes back down, over. Back. I'm just drawing one period of sine just for the hell of it. So there's one of my curves. Y equals x is the diagonal, isn't it? Again. So that's going to look like, something like this. X equals pi over 2 is what? But what is it? I mean, geometrically, what's x equals pi over 2? It's a vertical line. It's this right here. And x equals pi is another vertical line that goes this way. All right. Where's my region? The one bounded by all of those. Has to be bounded by all of them. Okay, so pi and pi half, so I've got to be between these two. Where, though? Above the red and below the blue. So I need to extend my blue out a little bit more. Does everybody see that this region is the one bounded by the 4 curves, even though 3 of them are straight lines? Everyone see that? So what happens on the test if you get the wrong region? It's all wrong, right? So you got to be very clear on what the region is. The types of functions that I would expect you know how to graph: exponential functions, log functions, sine, all your basic trig functions. Those all, you should be able to draw those without too much suffering. Polynomials, basic polynomials. All right. Questions? Vertical or horizontal rectangles? Vertical. Could you do horizontal? Yes, but it would suck because it would require you break it up into 3 separate integrals. you would have to do this one, because you would have this green one on top of the red one, and then it would be the green on top of the black, and then it would be the green on top of the blue. You see that? If you turn sideways, 3 separate ones. Way too much work. It's better to just grab a vertical rectangle here, because if I slide that vertical rectangle left and right in the yellow region, the blue is always on top, the red is always on bottom, isn't it? The whole time? Draw my rectangle out here to the side. I'm going to draw my blue curve coming across the top, my red curve coming across the bottom. These need to both be written as functions of x, because it's a vertical rectangle. So what's this top one? F of x is what? X. And then the red one, I'm going to call it g of x, and that is sine x. Now I need to find my endpoints, don't I? Oh, well, I didn't put what the height was, sorry. What was this height going to be then? X minus sine x, right? That'll be my integrand. And then dx is the infinitesimal width. But where do I start? Where does the yellow region start? Where does it end? And we're looking at x values now. And this one's obvious. You don't have to solve anything, do you? Where does it start? Pi over 2. Where does it end? Pi. So I've got the left and right endpoints. So I go set it up. Integral pi over 2 to pi of the integrand, which is the height of my rectangle, times the width, which is dx, equals dot, dot, dot. Is everyone clear on what I'm looking for on the test? I'm looking for a decent picture. I'm looking for some indication that you know where things are coming from and just setting up the integral. If these were not obvious, I would expect to see, you know, where you solve to get those intersection points. Questions, comments, concerns? Sketch the region bounded by x equals y to the 4th, x equals the square root of 2 minus y equals 0, and then find the area of the region. All right, so now we're getting into some more functions that are a little bit more challenging to graph because it may be something that you're not as familiar with. Both of these equations are solved for x, aren't they? Which makes you think it's probably going to be functions of y, which means you're going to want to use horizontal rectangles because they're solved for x. But let's just make sure we can graph them. What does x equals y to the 4th look like? It looks almost like a parabola, but it's a 4th degree. So 4th degree polynomials look like 2nd degree. They're just a little bit steeper. So we have something that looks like this. That's this. How about x is equal to the square root of 2 minus y? What does that look like? How are you going to graph that? You know it's a square root function, so it looks like a square root, right? Hold on. Thank you. But it's not a traditional square root because it's solved for x, so it's going to be going like like either this or like this instead, right? In the direction of y, but which one is it? So, you know, whenever you're in doubt, just try to plug in some points. Like plug in y equals 2. If y is 2, what's x? If y is 2, what's x? 0. So let's just plot that point. Y was what? 2, and x was 0. So that's like here. See my point? Plug in another point that would be easy to grab a value from. What's something you know the square root of? So you want to, you're not close. Hold on. How about, you know the square root of 4, right? Is 2. How can you make this a 4? Y is close. -2. If y is -2, you get 2 minus -2, which would be 4. Square root of 4 is 2. So if I plug in -2 for y, the x value is 2. Agreed? -2 for y, the x value is 2 is here. You see it? -2 for y, the x value is 2. Maybe one more point. Let's try one more. What's another square root you know? 9? How can you make this a 9 in here? -7 for y. If you plug in -7 for y, you're going to get 9 here. Square root of 9 is 3, so x would be 3. So plug in -7 for 9. 1, 2, 3, 4, 5, 6, 7. And you should get 1, 2, 3 for your x. And I think that that's enough for us to be able to determine that this thing goes like this. I hope that that's enough. Is that all right? And then y equals 0 is the next piece. What's y equals 0? Y equals 0 is the x-axis, which is there. That's it. What's the region bounded by? This is not going to make any sense. I'm going to have to adjust this problem. There's a mistake in here. I mean, it doesn't make sense because 2 regions are bounded by all 3, right? This region up here, isn't that bounded by all 3? And then the region down here is bounded by all 3 also, isn't it? So I'm going to modify the question. I'm just going to add one more thing up here. Okay, so that's our, just going to add in here to make it make sense. In 4th quadrant. Now what I've done, and this again will come up like in a problem on a test. If I say in the 1st quadrant, then you know that you're in the top right corner, right, of the plane. Here in the 4th quadrant means I'm down here, right? So I'm looking at this region right there. So got it? All right, so that was my first rough graph. So what I'm going to do is I'm going to draw it again real quick because I want to kind of blow things up. And I don't need to be super precise here. I had this square root function going like this. Then I had the parabola thingy looking like this. And I'm looking at this in here. Vertical or horizontal rectangles? Horizontal. If I draw a rectangle in here, horizontal, then I'm always going to have the blue on top, the red on bottom if we turn our heads. So I'm going to want to call the blue one what? F, right? F of y. And what is that one? Square root of 2 minus y, right? And then I want to call the red one g of y, and that one will be y to the fourth. I'm going to move my rectangle down here, draw it again, have some fun with it. This distance between the two is what? This is dy right here, yep. And then what's the width of that rectangle? Square root of, I'm going to do it on the bottom. Square root of 2 minus y, then what? Minus y to the fourth. What next? The bounds, the intersections, right? Anywhere, or limits of integration. So how about we need to find this point where they hit each other, and that'll be our C, won't it? So this is going to come over here. This will be C. What's D? It's this side right here, right? That's just y equals 0. Y equals 0. Remember, our limits of integration are our y values. So how are we going to find this C here? We need the intersection of what two things? The red and the blue, right? So square root 2 minus y equals what? Y to the fourth. How do you solve that? Square both sides, right? That's a radical equation. You square both sides of the equation. Remembering that anytime you square both sides of an equation, you always introduce the possibility of extraneous solutions. We'll have to check our answers when we're done. So square both sides, and you get 2 minus y equals y to what? The 8th power, right? Uh-oh. Now what? Let me move everything to one side, and maybe that'll help. Any ideas here? What's that? Did I not? Oh, plus. Oops. Thank you. It's not a quadratic, right? It's not a quadratic type either. Like if this was y to the fourth in the middle, that would be a quadratic type, and we could do it that way, but it's not. Any ideas? How about a it's a mathematical approach, but it's not what we would consider a very powerful approach, and that would be just inspection. Look at your picture. We drew a pretty good picture over here, and now really I don't know how good this picture was. Remember, this was -2, wasn't it, for y? Yes. So I don't know. What do you think? I mean, just by inspection, can you tell what would work? One would work, wouldn't it? One would work. What's wrong with that, though? Isn't that picking up the one up here? Y equals 1 is where they hit each other up here. How do we figure out where they hit each other here? Would -1 work? No, right? Negative 1 won't work. So this begs the question here, how do we solve this equation? I mean, if that's going to become our issue, right? I mean, it all boils down to this. If we can't solve that, we can't get our limit of integration, can we? So what are our techniques? What are our methods for solving things like that? And I'm just wondering if anyone remembers one other thing we can try. No? No? If it was quadratic or quadratic type, we could do it. It's not, though. There's another method in college algebra that we used. Now remember something called the rational zero test? See if this rings a bell. You get your polynomial in order, you look at the coefficient in the front, you look at the constant in the back, you create a list of numbers and you try synthetic division? No? Oh, okay. Rational, I'm just going to write it down here, zero test. What you do is you list out all the factors of all the different numbers that you can multiply together to get negative 2, which would be positive negative 1, positive negative 2, right? That's the only way you could get 2 using integers. You could do 1 times negative 2 or negative 1 times positive 2. And then you divide that by all the different ways that you can get 1, which would be 1 times 1 or negative 1 times negative 1. So all the factors of 1. And then from this, you take all the different possibilities. So you do positive and negative 1 over positive and negative 1, which means positive and negative 1, or you do positive and negative 2 over positive and negative 1, which gives you 2 more possibilities. So there's 4 possible rational zeros. And then what you do is you set up synthetic division. I'm only doing this because I'm trying to see if it's ever going to click in your mind that you remember this. Now I write out with synthetic division the coefficients of this polynomial, which would be 1, okay, x to the 7th power. Do we have one? Okay, so 0, that's 7th power. 6th power, 5th power, 4th power, 3rd power, 2nd power, 1st power, 1, and then negative 2. And then what do you use for the synthetic division on this? You have to try all 4 of these. So I'm going to try negative 1 work first because I know it's going to work. I do this, I get 1, negative 1, multiply 1, add down 1, negative 1, add down. What am I hoping to get at the end of this? A remainder at the very end of 0. Hold on. Did I do this? Did it work? Oh, shoot. You know what? 1's going to work. I'm sorry. I forgot it was 1 that worked. This won't work, will it? Because we get a remainder of negative 2. If you get a remainder other than 0, that means it didn't work. So now we try 1. Do y'all remember this or not? I mean, now that I'm doing it, do you remember seeing it ever? What's that? Yeah, I know. Okay, look it up. It's called the rational zero test. And now I'm going to use 1 out here. Because I'm not going to sit here and go through what synthetic division is. You're going to get 1s all the way down here. You're getting 1s. And then at the end you get a 2, and then when you multiply you get 2, and then here you get a remainder of 0. And what that means is that 1 is a factor of this, and if it's a factor, then that means that it's a solution to setting equal to 0. So 1 works. But if we try 2 and negative 2, I don't believe they're going to work. So that means the solution is not a rational number, which means it's irrational, which means this method fails. So what do? We go to Wolfram alpha, right? Solve it. Let's go to Wolfram alpha and solve it. Solve y to the 8th plus y, right? minus 2 equals 0. 1, okay, we had that, right? We knew that already. The other one is negative 1.15442. There's no way we would have gotten that. We don't have a method for it. And then we have 3 complex solutions, and that's because if you have an 8th degree polynomial, you have 8 complex solutions. So where are the others? There they are. Here they are. We're not getting into that. All right. So how in the hell is a computer getting y is approximately negative 1.15442? Anyone remember from Cal 1 how to get that? I'll give 3 points bonus on the test you just took if someone can tell me how to get that from Cal 1. Newton's method. Very good. Newton's method. Do y'all remember Newton's method? It was, no? You may not have seen it. It just depends on your instructor. It was a method that you use the derivative, the slope of the tangent line, to try and get closer and closer to an x-intercept. And that's the way a computer does it. And that's exactly what's happening here. So, the moral of this story here is, I'm never going to give you one that can't be solved, okay? This will never happen on a test. Could it happen in the real world? Yes. In a real world situations, a lot of times your numbers are never nice. So how do we go and find intersections? Well, we have to solve an equation. If the equation isn't something we can solve by hand, we have to do it with an approximation, and that's where things like Newton's method would come into play. So let's just wave our hands at this. You all know what hand waving is? It's kind of like surrendering, and just concede to the fact that we couldn't do that one, but we use a computer to get it. All right? So what would the integral then be? According to Mathematica, or Wolfram, was it negative 1.15442, something like that? Negative 1.15, I'll say, to where? Where did we stop it at? 0. And then what was the integrand? Was it the root one? Root 2 minus y? And then minus y to the 4th dy. Would have been a lot easier had I put this one in the first quadrant, right? If I would have done it in the first quadrant, we would have been able to do it by inspection. That is something I would expect you could do on a test. If this would have been in the first quadrant, that region up here, you would have found that point by setting up the same equation and then going, oh yeah, 1 works. What the heck is this? Yeah, that's one we just did. But I had them, when I set this up originally, I did the first quadrant instead of the 4th. So I cut this off. It didn't keep going, and this parabola kept like this. So this is a good one. I like this one. I just think this one's kind of interesting because of the way people interpret these two things. Misinterpret. Draw a picture. Okay, y equals x to the 4th looks like what? Parabola, kind of, right? Y equals x to the 6th looks like what? A narrower parabola, right? How do I draw it? Do I do this? Is it like this? Like narrower, like that? See, there's something interesting about this, and that's why I give it as an example. What do they both have in common? Both of them pass through the origin, right? And 1, 1, right? They both go through 1, 1. So if I plug in 1, let's just say this is 1, I should get 1 out. And also negative 1, 1. Do you agree? Both of those curves include all three of those points. The question is, on this one, between 0 and 1, is the x to the 6th above the red one or below the red one? Or do they hit each other in there? It's below it. And that's the part that people get lost on. Not lost, but they get incorrect. So look, if I tell you right now, plug 2 into this, what's 2 to the 4th power? Some number, right? What's 2 to the 6th power? Some bigger number. Yes? So if we're over here at 2 and we plug 2 in the blue one should be on top of the red one, shouldn't it? Out here at 2, because 2 to the 6th is bigger than 2 to the 4th. But try and plug a number in between 0 and 1 in, like 1/2. What's 1/2 to the 6th? Well, 1/2 to the 6th is the same as 1 over 2 to the 6th. Compare that to 1/2 to the 4th. That's 1 over 2 to the 4th. Which of these is bigger? One over 2 to the 4th is bigger. You have to be careful when you're looking at powers of things. All right? If you have a fraction like 1/2, if you raise it to the 2nd power versus raising it to the 3rd power, people always think, oh, you raise it to a bigger power, it's a bigger number. Not necessarily. If it's a fraction, it actually gets smaller. So our blue curve here, the x to the 6th, is below the red curve between actually -1 all the way to 1. That make sense? After you get outside of -1 and 1 on both ends, then the bigger power takes over. But you got to be past the 1 in each direction. All right, and then x is positive. What does x positive mean? To the right of the y-axis, so I'm throwing all that out. Y'all see my little region here? Yes? I'm going to do this without drawing any pictures. This is a vertical rectangle. Where's my integral going to start? Where's it going to stop? 0 to 1. Okay, it's going to be the top function minus the bottom function. What's the top function here? X to the 4th minus the bottom function, x to the 6th dx equals ... So that example was just to make sure you understood which is on top and bottom, comparing, being careful. I think for this one, I'm going to just pull the whole picture over, because I'm hoping that you've kind of picked up on this by now and you see what's required. All right, so sketch the region bounded by y is the square root, absolute value of x, and y equals x squared minus 2. So absolute value of x is the red v, right? So the red one, and then the blue one is the parabola. And I'm looking at this, and we run into a couple of issues because we haven't really integrated the absolute value of x before, have we? We've never integrated the absolute value of x. So I think it's a good time to just talk briefly about what the absolute value of x is. The absolute value of x is just a piecewise function. It's x if x is greater than or equal to 0. It's negative x if x is less than 0. That's all the absolute value is. So let's just interpret this. What does y equals x look like? Y equals x. Your diagonal, right? Slope of 1. It's saying that's what you are if you're bigger than 0. So you see this red part right here? That's your diagonal, slope of 1. That's what you are if you're at 0 or to the right. And then if you're to the left of 0, if x is less than 0, then you want to be the other diagonal that comes down with the slope of negative 1, and that's this side. And so you can really look at the absolute value as being two functions. It's this one and then this one. That being here and that being here. So with that said, am I going to use vertical rectangles or horizontal? I'm going to do vertical, here to here. Do you have a top function and a bottom function that stay the same? Yes, until I get over here, right, to the yellow, and then it changes, doesn't it? So I would have to split this into two integrals. Or can I just use the symmetry of the problem? I mean, the area to the left of the y-axis is equal to the area to the right, isn't it? Because it's symmetric. So why don't we do this? Why don't we double the area and we go x minus x squared minus 2 dx. So what this is this is the top function, which is the blue. Take away the bottom function, which is the parabola. I'm doubling this answer. So there's a 2 out here. My limit of integration is going to go from where to where? 0 to wherever these two intersect each other, which happens to be 2. And how would you get that? How would you get that? Set them equal to each other, but what would you be setting equal to each other? X squared minus 2 equal to what? X. Because you're trying to figure out where this diagonal hits the parabola, and that diagonal is just x. And then solving that quadratic, you're going to get 2 answers, but only one of them is going to make sense. So x is 2. Is this okay? I went a lot quicker through this one now that we've kind of got the setup. I would still want you to draw the pictures and get it all nice and clean, but in an effort to save some time, that's what we'd have. If you did not use symmetry, then you would have to use 2 integrals. The second integral is the same integral we just had, but we're not doubling it. But the first integral, your top function changes from x to negative x. So you see that the change here is this, the difference. That would give you the same result. A little more work, though. This is an interesting one. Sketch the region bounded by x equals sine y, x equals cosine y equals 0, y equals 2 pi. So let me start by first figuring out, what does y equals 0? Well, that's the x-axis right here. What is y equals 2 pi? Well, y equals 2 pi is up there, right? What does a sine function look like when it's written as a function of y? It's this one right here, isn't it? Isn't that it? That's your sine? And then what does your cosine function look like? It's this blue one. You got to be careful because it is not this. Oops. People will think this. Oh, if I'm going to do a sine function up the y-axis, it just looks like that. What's wrong with it? What's wrong with this? Your first arc of sine should be positive numbers, right? And here, your x values are negative. You want it to be positive x values, then negative x values. It's kind of interesting. I don't want to go too far on a tangent here, but this is our standard xy, right? If I want to switch the variables, if I just want to come in here and say, hey, look, I want this to be y and this to be x, switch them around, then does my picture look the same? So I just told you it has to look like this, right? If this is y and this is x. That's what it looks like. This is x equals sine y. This is y equals sine x. And what I'm claiming is that these are pretty much the same thing. So imagine I'm sitting here, I'm looking at the first graph, positive x, positive y, right? Like this. Arc goes up, then down. Now, if I go over here and I turn my head to the right, then the positive is the other way, isn't it? Like this way. Up is still positive, but positive this way. So if you want this picture here to look the same to your eye as that one, you actually need to go out the room, go to the other room, and imagine that this board is transparent, and look at this picture from the other room and turn your head this way. If you do that, what would it look like? This. Wouldn't it? You have to, I don't know if you can visualize that or not. Right? This is the same as being in the other room looking at that this way. And so all you're doing really is just doing like a rotation followed by a flip. So anytime you can take a space, like a flat sheet of paper, and you can just move it, translate it, or rotate it, reflect it, and it still maintains everything, it's called an isomorphism. Isomorphism. Yeah, I haven't used that word in so long. The reason I'm bringing this up is because three-dimensional space does not work this way. Because what I'm telling you is this. You can always just take x and y and switch them anytime you ever want to. Like if this problem right here, if you were not happy with this problem, because your graphing calculator can't do this, you could just rewrite the entire problem, y equals sine x, y equals cosine x equals 0, x equals 2 pi. As long as you've replaced every x with y and every y with x, you'll get the same exact answer. That will always work with two-dimensional space. With three-dimensional space, it does not work. And for those of you who've done some physics and stuff and maybe more math, you have this thing, three-dimensional space looks something like this. And you have what's called the y'all ever seen that? Right-hand rule. The right-hand rule, y'all know what I'm talking about? Right-hand rule says that when you draw a three-dimensional space, your thumb should point in the direction of the positive z-axis, and then your fingers should curl from the positive x to the positive y. So it's like, imagine I'm in the corner of the room over there. The z is going up the wall. Then that wall over there is my x-axis, and I curl my fingers into this side, which is the y-axis. That's the standard way that we draw three-dimensional space. If I come in here and I just say, okay, look, I just want to switch y and x, does that still follow the right-hand rule? No, because if I point my thumb in the direction of the positive z, my fingers do not curl from positive x to positive y. This is no longer the same space. You cannot just switch variables in 3D. It's a big deal. We can do it in 2D, but not in 3D. What would I have to do in order to make that work? Could I? Where would I have to put Z, positive? Down here? Now my thumb has to point down, and look at the way my fingers curl from the positive X towards the positive Y. Do y'all see that? I remember when I was in a class, it was called non-Euclidean geometry, and I was doing some problem, and I couldn't get the answer. I went up to the professor, and I was like, can't get this one. You know, I'm sitting here. I'm like, she's like, that's your left hand. I was like, shit. Because I'm left-handed. So I was like, you know, doing everything on my left hand. Right-hand rule. All right, so back to this. This is the proper drawing of sine and cosine. So if we want the area, you would first have to figure out which one's on top and bottom, right? So I would do horizontal rectangles, right? Horizontal, horizontal, horizontal. But there's three different ones because they switch places. In this first little area, the cosine's on top of the sine, isn't it? And then it switches to the sine being on top of cosine, and then cosine on top of sine. So you would have to break it into three integrals. Where would the breaks occur? Wherever these two intersect, right? So you have to set cosine and sine equal to each other, solve that trig equation on the interval 0 to pi, and you would get the solution pi over 4, 5 pi over 4. And then you'd have your two endpoints. So do y'all see the integrals that would be set up here? Sketch the region bounded by y equals e to the x, y equals 2e to the negative x plus 1, and x equals 2. I think the challenge in this one would be the actual sketching, because perhaps some of these are not as obvious as the others. We're all comfortable with e to the x. We better be, right? That's this one, the red one. I think we're all comfortable with what x equals 2 is, vertical line. But what about the 2e to the negative x plus 1? The way you do that is you have to know what e to the negative x looks like. When you have a negative in front of the x, instead of it looking like this, it's what? Reflected over the y-axis. So it's this red one reflected over the y-axis, but then you multiply by 2, which has the effect of what? Stretching it out vertically, just making it longer. And then what does the plus 1 do? Shifts the whole thing up 1. So you have blue curve going like this. And then you can see the region bounded. Would you want vertical or horizontal rectangles? Vertical? Yeah, I think like this, right? Because that red one's always on top of the blue. Which means my integral would, I'll get the limits of integration in a second. It would be the e to the x on top, and then I'm going to take away from that the other one, which was 2e to the negative x plus 1 dx. Do I have one of my limits of integration? 2, right? The right side where this area ends is 2. The only question is, what's the left one? Am I moving too quick through this? I mean, I know the first ones I showed as much detail with the, simple functions, but am I going too fast through this, or are y'all okay? Just doesn't matter? All right. I don't know why. I just got this mental image of, I went and saw this movie with my daughter, my 5-year-old. What's that movie with that little? The character's name is O or something like that. It's an animation. No, I'm sure y'all haven't seen it yet. But what is it? Home? Yeah, is it Home? The little alien guy. Okay, there's like a scene where the mothership comes down and just starts tearing up the earth. You know, that's what I'm visualizing right now. Is just me just tearing through, and everyone's just like this, and it's just. I mean, I don't know. That's the look I'm getting, but I'm not sure if that's what's happening. I don't want to go too fast, but I also don't want to bore you to death if you understand the idea here. It's hard to sit through, right? You know what I suggest you do is just remind yourself why you signed up for the class. I mean, I say the same thing every summer. I don't know why someone would want to do 2 hours and something minutes. It's hard to sit through anything for that amount of time. 3 hours. Is it 3.5? Oh, shit. You know? I mean, it's tough, right? But it's also only 8 weeks. 8 weeks of suffering. What about the intersection? What are you going to do here? Set them equal. And I believe this is going to be a nice exercise. How do you solve that equation? So these are the things that I'm afraid are going to pop up for you, because this is natural in Cal 2, is that all of a sudden all these weird things from algebra just start appearing. You want to take everything to one side? I have no complaint on that. That's fine with me. Now what? That's not illegal. That's perfectly valid algebra move. Trying to solve for x. You can do a natural log, does wipe out an e to the x. Problem is you have 3 terms, so you can't just take the natural log on the left side, because you have natural log of all 3 terms, and it doesn't distribute to each one. Because natural log isn't like a number that multiplies through. You'd be taking the natural log of the whole side. Anyone? Clear out the fractions. Okay, so let's clear fractions. Multiply this by e to the x. What's e to the x times e to the x? E to the x squared. Minus, what do you get when you multiply this by e to the x? 2. And then what happens when you multiply -1 by e to the x? Equals 0 times e to the x, still 0. And then if I rearrange things, that is a what? Quadratic type problem, right? I could do like a quick substitution. I'm not doing integration right now. I'm just doing quick substitution. If I replace every e to the x I see with u, it's u squared minus u minus 2, isn't it? Equals 0. That's a quadratic now. And so I factor it. So you get 2 solutions. U is 2, u is -1. But I have to switch u back. So this is the same as saying e to the x is 2, and e to the x is -1. Now you're free to take natural log on both sides, because these are 2 separate equations, right? So when you take the natural log of the left side, what do you get? X, and then you have to do the same thing to the right side, so natural log 2. Then over here you get x is natural log of -1, but natural log of -1 is undefined. So you only have one real solution, and it's natural log of 2. And so that's our other limit of integration. Questions? That's it. Okay. Time do we end? 12:30? Seems like we always end 20 minutes before, and then I always say, okay, I think that's good. And y'all are super tired, but we gotta go another 20. I'm sorry. They took Thursday away from us. I need to at least start what we're going to be moving into. You want homework for that, don't you? Of course you do. Of course you do. I like 1 through 19 on page 369. I would encourage you to just work on setting them up. Set up, set up, set up, set up, set up, and then if you have the time, go try and get the answers. All right, I believe that I don't have notes for anything else out there. Is that correct? That's right. Okay, so as far as the notes that are out there online for you to print out and bring to class, from here on out, it's pretty much what I put up here, and the reason is because the notes are very geometric. I find it easier to write them down than to try and print them up. And it's not like we're going to have a whole bunch of notes. Very simple formula, not simple formulas, but very basic ideas, and then just some examples. All right. 7.2. Volumes. And I'm also going to put next to this, sometimes you'll hear this called solids of revolution. And the methods that we're going to employ in this section are called disks and washers. All right, so to start this out, I'm going to try and structure my notes as much as I can like I have been. 721 is something to remember, okay, recall. That if somebody were to give you a cylinder, right? If someone were to give you a cylinder, now that's a right cylinder, it's not like leaned over or anything, it's not parallelogrammed. Then if you wanted to know the volume of it, you would have to know a few things. The volume of this would be the area of the top. What's the area of the top? Well, you would have to know the radius, wouldn't you? So this right here being R, the area of that top piece is pi r squared. And then you just multiply that times the height of the cylinder, and that's your volume. So imagine it being the area and then times the depth of the area. So pi r squared h. Yes? Okay. Then if we take something that looks like this, and we say we have like a radius that goes on the outside, let's call that R out. And then you have a radius on the inside, which is the smaller circle. I know it's hard to read, R in. Can y'all see that? Understand? Then what would the volume of this be? Now we're imagining this is like a solid cylinder where you've drilled a hole out of the middle of it. So what's the volume of that? The outer volume, I'm going to draw a little thing going through here. Okay, so that's what you can't see on the inside. It's drilled out. And then subtract the smaller one, right? Okay, so the volume of this would be the volume of, let's say, the outer one minus the volume of the inner one. And what is the volume of the outer one? Pi R out squared times H minus pi times R in squared H. And what do these both have in common? Pi and an H. So let's factor out a pi and an H. And it would be R out squared minus R in squared. Everyone agree? Everyone understand? Now, one last thing. I didn't label H over here. One last thing. On these cylinders, when we normally draw them, you know, they have pretty big heights to them, right? I mean, like we imagine a can or something like that. But there's nothing that says that that height has to be tall, right? It doesn't have to be very tall. So if I were to have drawn this picture right here, this way, everything would still be the same. Right? The volume would still be pi times H times the outer radius squared minus the inner radius squared. Yes? And the height's just real small. All right. So with that in mind, let's get into what this whole volumes and solids of revolution is all about. We wish to rotate the region bounded by two curves about the x-axis. So you know how we were just finding the area of the region between two curves? What we want to imagine now doing is taking that region and rotating it around the x-axis. So I have an animation here, I believe. See if I can find it. Sorry, I thought I had it. So right now I had two curves, but it only looks like one. I have this curve here, right? And then the other curve is just the x-axis. What I want to do is take the region bounded by the two, which is the area between those. I want to rotate it around the x-axis. When I do that, I create a three-dimensional figure, don't I? A three-dimensional object. And three-dimensional objects should have volumes to them. So I haven't used this in a while. Imagine now that we're going to snap this thing out of two-dimensional space into three-dimensional space. You see it? And then I'm going to take a rectangle. I'm going to widen it out so you can see it. You see that rectangle that we had? That was the rectangle that we used to find the area. And I'm going to rotate that around the x-axis. And when I do that, what have I created? This disk, right? It's a cylinder. It's just laying sideways instead of the way we like to draw our cylinders, right? But it's a cylinder. And so if I knew the volume of that one cylinder and then moved the rectangle over and found another one, wouldn't I get the volume of the whole thing? Yes? So it's going to involve an integral. It's an infinite sum. As I move the rectangle, as I move the rectangle though, notice that the cylinders are changing, right? As I move out here to this edge, that cylinder is smaller, less radius than the one before. Now I think I have below this what you would get if you put them all together, right? This is the solid we're talking about. And so we want the volume of this, almost looks like a football. Yes? So we can find a formula for this, for that rectangle being wrapped. If we can find a formula, then we can do it for any functions. Geometrically, though, we good? Okay, so I'm going to start with an arbitrary picture here. Here's my x-axis. I'm going to have a function on top, which I will call f of x. I will have a function on the bottom, which I will call g of x. I will take this rectangle that we used to find for area, used to use to find area, and I want to wrap it around the x-axis. Okay? So I'm going to come over here to the side just like we did before. Here's my x-axis. Here's my rectangle. All right? We know that this distance here, I'm just going to put f minus g. Is that all right? Instead of f of x minus g of x? F minus g. Let's go ahead and throw our limits of integration on here. They're a and b. We don't know what they are. There's some numbers. Wrap this thing around the x-axis right here. So I need to somehow let everyone know I'm wrapping it around the x-axis. So we usually use like this curled arrow. See that curled arrow I put around the x-axis? That just lets everyone know I'm rotating around the x-axis. Because what do you think comes after x-axis? Wrap it around the y-axis. And then after that, you can wrap it around any line, vertical or horizontal. Doesn't have to be an axis. So there's my drawing. My axis of rotation is right here. And remember, I'm always trying to set you up for what's coming. Real quick, my axis of rotation is horizontal, right? My rectangle is vertical. Do you agree that my vertical rectangle is perpendicular to my axis of rotation? Whenever you have your rectangle perpendicular to your axis of rotation and you rotate, you're going to get that picture we just had. You're going to get, this right here would be considered the disk. Imagine flattening that out. I never showed you the flat version of that. That would be a disk, right? Like a coin, a disk. This right here, flattened out, looks like a what? A washer. So this is the disks and washer method. Sorry, I should have pointed that out. Sorry. So if I wrap this, my vertical rectangle, perpendicular to my axis of rotation, if I wrap that, I'm going to get a disk or a washer. In this case, it's going to be a washer, right? Later on, we're going to use a different method called the method of shells. And for that one, you want your rectangle and your axis of rotation to be parallel. When they're parallel, you use a different method. Okay, so let's wrap it. Wrap it up. Let's go. So how do we do it? You just try and draw a picture, okay? That's not good. Man. something like that. My x-axis is going right through here. Do you see the rectangle in here? Do you see the rectangle in there that got wrapped around? You do not have to draw me a really, really good 3D picture, but if you're going to do more engineering, math, whatever, just, I mean, you want to try and get better at it. So practice it. This stuff up here you should draw, be able to draw. All right, let's talk about this volume. The volume of that one little sliver. What's the volume of it? Well, we know it's pi h r out squared minus r in squared, right? What's my outer radius? What's the outer radius? What's the distance from here all the way down to the axis of rotation? That's f of x, isn't it? What's my inner radius? That's from here to here, right? G of x. Do you all see that? F of x is the outer radius. G of x is the inner radius. You could see it up here too. This was G of x, and F of x was the whole way. Now, with area, we just wanted to know what F minus G was, right? With area. But now we want volume, so we actually have to account for the radius, not necessarily the difference. We need the actual radius. So it's F is our outer radius, and then G is our inner radius. And then what is H? It's the width of this thing, which is dx. Right? It's the infinitesimal width of the rectangle. So give me a volume for that sliver of formula. Pi. Let's throw the dx on the outside. That's our h, right? And then what's in here? F of x. We write squared here, minus g of x squared here. So these little squares on these mean you square them, right? The important thing here, people get tripped up on, is they think that you take f minus g, then square. No. You square f, square g, then subtract. So you have to do order of operations. Squaring of these first, then do the subtraction. You with me? That's the volume of one sliver. We want all of them, don't we? Let's add them up. So this is where we're going to get our master formula here. The volume of the entire thing. So this is the volume of a slice, right? Just one slice. This is the volume of the whole thing. Will be pi, because it's a constant, can come out. Integral adds them all up from where to where? A to B of f squared minus g, let's do f of x. Squared minus g of x squared dx. That's it. I have 15 minutes. I want to see if I can blow your minds a little bit in 15 minutes. No, wait. 4 minutes. I don't have enough time to blow your minds in. 3 minutes. Next time. Damn it. All right, well, this is where we'll pick up. Just remember this. Don't come in cold. That's where we'll... This is washers. The only time you would have a disk is if your g of x was the function 0. Because then you're using the x-axis, so you don't really have that inner part to take out. Okay? All right, well, I guess have a good holiday, and I'll see you in a week. Sign-in sheet, is everybody here? Yeah, everyone's here. No, I can tell by who didn't pick up their exams. Anyone not pick up their exam? Or what?